Hello students, in this video let us discuss the mechanism of nucleophilic substitution reactions in the chapter haloalkanes and haloarenes. Please like, comment and share. Subscribe to my channel. Nucleophilic substitution reactions. Alkyl halides undergo nucleophilic substitution reactions. In alkyl halides or haloalkanes, the halide ion is already present as a nucleophile. The existing nucleophile is replaced by other nucleophiles like hydroxyl ion, cyanide ion, etc. Nucleophilic substitution reactions are of two types. They are SN1 and SN2. SN1 is a nucleophilic substitution reaction involving only one molecule in rate determining step or slow step, whereas SN2 is a nucleophilic substitution reaction in which two molecules are involved in rate determining step. Mechanism. What is mechanism? Mechanism is a detailed discussion of a reaction. Detailed discussion of a reaction in two or more steps. Two or more steps. The detailed discussion of a reaction in two or more steps is known as a mechanism. Generally, mechanism has two steps. Two steps. One is slow step or rate determining step. Rate determining step or slow step. The second one is, next step is completion step. Completion step. This is rate determining step. This is completion step. Because of this first step, that is slow step only, we can determine the rate of the reaction. If the rate determining step has only one molecule, the order of the reaction is 1, that is first order reaction. So rate step or slow step, if rate step has one molecule, then order is first. If the rate step has two molecules, then it is second order. Second order. SN1 mechanism. SN1 mechanism. SN1 mechanism is, this mechanism involves only one molecule in the rate step. Rate step has only one molecule. What is rate step? Slow step. Rate determining step or slow step, both are the same. Now let us take tertiary butyl bromide. This is tertiary butyl bromide. Tertiary butyl bromide. What is tertiary butyl bromide? This carbon is the carbon bearing halogen atom. The carbon bearing halogen atom is connected to 2-3 more carbon atoms. So such a carbon is known as a tertiary carbon, and of course this substance is referred as a tertiary butyl bromide or tertiary alkyl halide. Now this halogen atom removes. So this is a reversible reaction. So here, as a bromide ion comes out, this becomes, the carbon atom gets a positive charge here. So it is in this way. Therefore, this is referred as tertiary carbocation. What is carbocation? If the carbon atom has a positive charge, it is referred as carbocation. Plus Br minus. The positive charge establishes on the carbon atom. This positive charge is subsided by the electron releasing nature of these alkyl groups. Alkyl groups have the nature of electron releasing. So electron density releases towards this carbon, and from here electron density releases, and from here also electron density releases. So this carbon atom bearing positive charge, this carbon atom gets the electron density from these three carbon atoms, therefore this positive charge is minimized. As the positive charge is minimized, its stability increases. Therefore tertiary carbocation is more stable. On the other hand, secondary carbocation is C, Br, H, CH3, CH3. This is a secondary alkyl halide. Secondary alkyl halide means carbon bearing halogen atom is connected to two more carbon atoms. This is CH3, this is CH3. So if it loses one bromine atom, C plus H, CH3, CH3. So this is secondary carbocation. In this secondary carbocation, the electron density is released by only two methyl groups, whereas in tertiary carbocation, this is tertiary carbocation. In tertiary carbocation, the electron density is donated by or released by three alkyl groups. Therefore, here the compensation of positive charge and carbocation is subsided to large extent when compared to here secondary carbocation. On the other hand, primary carbocation means this is CH2 plus CH3. So carbon bearing positive charge is connected to only one alkyl group. Here the compensation of positive charge present on carbocation is still less. Therefore the formation of carbocation is greater in tertiary, greater than secondary, greater than primary, greater than methyl carbocation. Therefore tertiary carbocation forms quickly when compared to secondary and primary. Therefore as carbocation forms quickly, the reaction goes faster. The nucleophilic substitution reaction involving tertiary alkyl halide goes faster when compared to secondary alkyl halide than primary alkyl halide than methyl halide. Thus, reactivity of alkyl halides through SN1 mechanism follows the order, follows the order, that is tertiary is greater than, secondary is greater than, primary is greater than methyl. So this is the order of reactivity of alkyl halides through SN1 mechanism. Now let us discuss the reactivity of allylic halides towards SN1 mechanism. What is allylic halide? See, this is CH2Br. Carbon bearing halogen atom is connected to sp2 carbon. So this is sp2 carbon, this is sp2 carbon. So this carbon bearing halogen atom is connected to sp2 carbon. Therefore this compound is known as allylic halide, allylic bromide or allyl bromide. What is the IUPAC name? This is carbon having double bond. So double bond is present on first carbon, bromine atom is present on third carbon. Therefore this is 3-bromo-prop 1 ene. 3 bromo prop 1 ene. So this is allyl bromide. So when this allyl bromide loses halide ion, that is bromide ion, then we get CH2 double bond CH, CH2. Positive charge forms here. Therefore, this is allylic carbocation. Allylic carbocation. So in this allylic carbocation, this positive charge shifts to this carbon atom. Therefore, we get CH2 single bond CH double bond CH2. So positive charge comes here. Therefore, these two are resonance structures. So the allylic carbocation is resonance stabilized, whereas previously we discussed about tertiary, secondary and primary carbocations. In those carbocations there are no resonance structures. Only the positive charge is compensated by the electron releasing by alkyl halides, whereas the positive charge is distributed on two different carbon atoms and resonance structures. Therefore, allylic carbocation is more stabilized when compared to normal carbocation. Thus, allylic halides undergo SN1 mechanism more faster when compared to alkyl halides. Now let us discuss the SN1 mechanism in benzylic compounds. Benzylic halides. What is benzylic halide? This is benzene ring. In benzene ring, this is alkyl group, and to this alkyl group one halogen atom is present. Therefore, this is benzyl bromide. Benzyl bromide. So in this benzyl bromide, if it loses bromide ion, then what do we get? This is CH2 positive charge formed here. This is benzylic carbocation. Benzylic carbocation. So in this benzylic carbocation, this this bond shifts here. Therefore, we get benzene ring. So because this bond shifts here, this gets double bond CH2, and because this bond shifts here, this center gets positive charge. So this is one resonance structure. Now in this bond shifts here, therefore we get, so as bond shifts here, this center has positive charge and the bonds are in this manner, CH2. This is another resonance structure. Now in the next structure, this bond shifts here, therefore we get in this way. So here bond comes here and comes here, and this is CH2 plus here. Now what happens in the next structure? This bond shifts here, therefore we get in this manner. So like this. So CH2 plus. So here what happens? We have 1, 2, 3, 4, 5. Totally 5 resonance structures. Greater the number of resonance structures, greater is the stability of carbocation. Therefore, benzylic carbocations or benzylic halides, because the benzylic carbocation is more stable when compared to allylic as well as normal carbocations. So this benzylic halide undergoes SN1 reaction quickly or faster. Quickly or faster. Now let us see how SN1 reaction goes. SN1 mechanism, SN1 reaction. So this is carbon attached to halide ion. This is CH3. This is hydrogen. This is of course, this bond is represented as a solid wedge. So in this molecule, the bonds are understood as the lines, the bonds shown by lines, they lie along the plane of the paper or plane of the screen. The dotted line represents the bond behind the plane of the board or screen, and the solid wedge, this is the thick one, it is solid wedge. The solid wedge bond is it is in front of the plane of the paper or screen. So this is the three-dimensional arrangement of the molecule. And of course, when it loses halide ion, this gets carbocation, and here this is CH3, this is H, and of course this is solid wedge C2H5. This is a tertiary carbocation. Now this tertiary carbocation, this is CH3, and the attacking nucleophile. So this is a dotted line, and this is a solid wedge C2H5OH, and here the attacking nucleophile, say OH. When OH attacks here, and of course the product is in this manner, COH, this is OH, and here this is a solid wedge C2H5, and here this is a dotted line, and of course this is so the lines, the bonds represented by normal lines, they lie along the screen or paper. The dotted line shows the bond behind the screen, and of course the solid wedge shows in front of the plane. And of course here, if the nucleophile attacks on opposite side, then we get in this manner. So this is a solid wedge C2H5, and this is a dotted line, and this is CH3, and here in this manner. See, this compound and this compound, the formula are same, but this compound is exactly the mirror image of this compound. So this is number 1 and this is number 2. So number 1 is mirror image of number 2, but they are mirror images. So these two compounds are mirror images, but they cannot be superimposable. Superimposable means we cannot keep one molecule on the other. So such compounds, the non-superimposable mirror images, are referred as enantiomers. So enantiomers, the main characteristic of enantiomers is they rotate the plane polarized light in opposite directions but to equal extent. Thus the angle through which the plane polarized light rotates by one enantiomer is exactly compensated by the other one. Therefore, the net rotation is 0. Thus, we call the mixture of two enantiomers is referred as a racemic mixture. And of course, the formation of two enantiomers is referred as a racemization. Therefore, through SN1 mechanism, there is a possibility of formation of racemization to some extent. Now let us discuss about SN2 mechanism. What is SN2 mechanism? Nucleophilic substitution reaction involving two molecules in the slow step or rate determining step. So, two molecules are involved in rate step. Right. So here, as two molecules are involved, what are the two molecules? This is bromine, and here this is one hydrogen, and this is here. So this is a solid wedge. This bond is in front of the plane of the screen. This dotted line is behind the plane of the screen, and of course this normal lines, the bonds showing normal lines, they lie along the screen. Right here, what happens? The nucleophile Z minus means attacking nucleophile. Attacking nucleophile comes and attacks. So here what happens? This existing nucleophile, that is bromide ion, that is halide ion, slowly it detaches. Simultaneously the incoming nucleophile slowly attacks, that is attaches. Therefore the formation is in this manner. So this is a solid wedge hydrogen, this is dotted line hydrogen, this is a normal hydrogen, and of course here we represent this dotted Br, this is a leaving group, this is leaving group, whereas this is attacking, this is attacking nucleophile. Therefore what happens here? For carbon there are 5 species are attached, out of which 2 are partially attached. One is a leaving group and another one is a attacking group. So here what happens after some, so this is referred as transition state. This is called as transition state. This is transition state is unstable because there are 5 bonds, right? Since it is unstable, it cannot be isolated. Transition state cannot be isolated, like a carbocation. So what happens? This leaving group goes out and attacking group attaches completely. Therefore we get in this manner. See, so here solid wedge hydrogen, this is dotted line hydrogen, and this is normal hydrogen. That is, this hydrogen, this normal line hydrogen is in plane of a screen, whereas dotted line hydrogen is behind the plane of the screen, whereas solid wedge hydrogen is in front of the plane of the screen. So here what happens? This configuration entirely changes. That is inversion from here. This is reactant molecule, whereas this is a product molecule. See, the reactant molecule and product molecule, what happens? The complete inversion takes place. So this is a SN2 mechanism. In SN2 mechanism, what happens? Alkyl halide RX as well as nucleophile, attacking nucleophile, both are taking part in the slow step, or simply it is a single step reaction. Why it is single step reaction? Because leaving group goes and simultaneously attacking group. Leaving group goes out and attacking group comes in. Therefore simultaneously both are taking place. Therefore it is a single step reaction. In this single step reaction 2 molecules are taking place. Therefore it is second order reaction. It follows second order kinetics. Therefore what is the rate? Rate equal to K into Rx, that is concentration of alkyl halide and concentration of incoming nucleophile. So it is a second order reaction, right? So in case of tertiary alkyl halides, In tertiary alkyl halides, what happens? Tertiary carbocation forms. So the bulkier groups, so this is CH3, CH3, CH3. So this is a tertiary carbocation, and these three methyl groups are bulkier groups. Bulkier groups means they occupy space. Therefore, the bulkier groups are attached to carbon carrying a halogen atom, makes the transition state unstable. So this transition state unstable towards SN2 mechanism. Remember, SN2 mechanism. Steric hindrance increases. Therefore, tertiary carbocation undergoes SN2 to least extent. In the previous slide, we discussed about the SN2 mechanism with respect to tertiary carbocation. So here, this is a tertiary carbocation plus, and of course this is the leaving group, and this is attacking group. This is attacking group. This is leaving group. So here, what happens? Attacking group and leaving group, they simultaneously attach to the carbon atom, carbocation, and at the same time the three alkyl groups are bulkier groups. Therefore, the incoming nucleophile is opposed, doesn't come quickly because of the bulkier groups. That's why the reactivity is less. Therefore, the order of reactivity of alkyl halides through SN2 mechanism is as follows. Primary carbocation or primary alkyl halide is faster than secondary, is faster than tertiary. So this is the order of reactivity of alkyl halides through SN2 mechanism. Now let us see an example. Minus bromooctane. What does this minus indicate? This minus indicates levorotatory. Levorotatory means this substance rotates the plane polarized light to left side. So when bromooctane is allowed to react with, say, NaOH, therefore what do we get? We get plus octanol, OCTANOL, octanol. OL means alcohol. So this bromide nucleophile is replaced by hydroxy nucleophile, and of course we get a substance. This is a reactant substance. So what is this reactant substance? We represented a plus sign in front of it. What is this plus? This plus indicates dextrorotatory. That is, dextrorotatory means it rotates the plane polarized light to right side. Therefore, inversion of configuration takes place in a SN2 mechanism. Differences between SN1 and SN2. SN1, it is the nucleophilic substitution unimolecular reaction. That is, the slow step involves only one molecule. SN2, nucleophilic substitution in two molecules or bimolecular reaction in which the first step involves two molecules.
It is carried in two steps, the slow step and fast step, whereas in SN2 there is only one step. First step involves one molecule, whereas in SN2 the one and only one step involves two molecules. In SN1, carbocation forms which can be separated. In SN2, transition state forms which cannot be separated. In SN1, inversion of configuration does not take place, whereas racemization is possible. In SN2, inversion of configuration takes place since the attacking nucleophile attacks opposite to that of leaving nucleophile. Leaving group leaves first and then attacking group attacks. Leaving and attacking groups leave and attack simultaneously. In SN1 mechanism, the order of reactivity of alkyl halides through SN1 mechanism follows the order tertiary is greater than secondary is greater than primary, and it follows first order kinetics. In SN2, the reactivity of alkyl halides through SN2 mechanism follows the order primary alkyl halide is greater than secondary is greater than tertiary, whereas it follows the second order kinetics. Thank you.